history made 50 years ago this week, right here in this room. This is Apollo 11 Mission Control in Houston, where they guided those astronauts who would land on the moon.
Many people know the names of the first two astronauts to walk on the moon. However, there was another astronaut working hard in the background to ensure the mission was a success. And before his death, the third astronaut revealed declassified images from the moon that changes everything we thought we knew about the moon. In this video, we bring you all the details of the revelation by these phenomenal Apollo astronauts. The following quotes are some of the most profound ever made in the history of the universe. I am alone now, truly alone, and absolutely isolated from any known life. I am it. If a count were taken, the score would be 3 billion plus 2 over on the other side of the moon, and 1 plus God knows what on this side. I don't mean to deny a feeling of solitude. It is there, reinforced by the fact that radio contact with the Earth abruptly cuts off at the instant I disappear behind the moon. I am alone now, truly alone, and absolutely isolated from any known life. Behind me is a black sky. Ahead is a totally new world. I feel like a Roman god riding high above all these people. These powerful quotes came from Michael Collins, one of the few humans to have close interaction with the other side of the moon. He was one of the crew of the Apollo 11 mission. In many ways, the statements are a culmination of the fierce battle between the US and the Soviet Union, dubbed the space race. The space race with Russia was a fierce competition between the two superpowers of the Cold War era, the United States and the Soviet Union, to achieve dominance in space exploration and technology. It began in 1957 when the Soviet Union launched Sputnik 1, the first artificial satellite to orbit the Earth. This shocked and alarmed the American public, who feared that the Soviets had gained a significant advantage in missile capabilities and scientific knowledge. The US government responded by creating NASA and the National Aeronautics and Space Administration, and investing heavily in research and development of rockets and spacecraft. The space race intensified in the following years, as both sides achieved remarkable feats of engineering and exploration. The Soviets sent the first human, Yuri Gagarin, into orbit in 1961, followed by the first woman, Valentina Tereshkova, in 1963. They also launched the first probes to the Moon, Venus, and Mars, and performed the first spacewalk in 1965. The Americans, meanwhile, developed the Mercury and Gemini programs to test human endurance and maneuverability in space. They also pioneered the use of rendezvous and docking techniques, which would be essential for future lunar missions. However, the ultimate goal of the space race was to land a human on the moon, which was seen as a symbol of scientific achievement and national prestige. President John F. Kennedy announced this ambitious objective in 1961, challenging the nation to landing a man on the moon and returning him safely to the Earth before the end of the decade. To accomplish this, NASA initiated the Apollo program, which involved designing and building a new generation of spacecraft and launch vehicles capable of carrying 3 astronauts to lunar orbit and landing 2 of them on the surface. The Apollo program faced many challenges and setbacks, including a tragic fire that killed 3 astronauts during a test in 1967. However, it also made significant progress and breakthroughs, such as testing the lunar module in Earth orbit and sending a crew around the moon in 1968. The Apollo 11 mission was the culmination of years of hard work and dedication by thousands of engineers, scientists, technicians, and astronauts. It was launched on July 16, 1969, from Kennedy Space Center in Florida, using a Saturn V rocket, the most powerful rocket ever built. The crew consisted of Commander Neil Armstrong, Lunar Module Pilot Buzz Aldrin, and Command Module Pilot Michael Collins. After reaching lunar orbit on July 19th, Armstrong and Aldrin separated from Collins in the lunar module Eagle and began their descent to the surface. They faced several difficulties during their landing, such as finding a suitable site amid boulders and craters, running low on fuel, and dealing with computer alarms. However, they managed to touch down safely on July 20th at a location they named Tranquility Base. Armstrong became the first human to step onto the moon's surface. He uttered the famous words, "That's one small step for a man, one giant leap for mankind." Aldrin joined him 19 minutes later, and they spent about 2 hours outside their spacecraft, collecting rocks, planting a U.S. flag, talking to President Richard Nixon via a telephone link, and performing scientific experiments. They also received a plaque that read, "Here men from the planet Earth first set foot upon the moon July 1969 AD. We came in peace for all mankind." They then returned to Eagle and lifted off to rejoin Collins in Columbia, which had been orbiting the moon for more than 21 hours. The 3 astronauts then began their journey back to Earth, splashing down in the Pacific Ocean on July 24th at 1650. They were recovered by USS Hornet, an aircraft carrier that had been waiting for them with a large crowd of sailors and media representatives. The Apollo 11 mission was a historic achievement that marked the end of the space race with Russia and demonstrated the power of human ingenuity and cooperation. It inspired millions of people around the world with awe and wonder and opened new possibilities for exploration and discovery beyond our planet. It also fulfilled Kennedy's vision of reaching the moon before 1970, as well as honoring those who had sacrificed their lives for the cause of space exploration. As Armstrong later said, "I think we all like to be recognized not for one piece of fireworks, but for the ledger of our daily work." Landing on the moon was not merely a step for man, but a giant leap filled with monumental challenges and intricate complexities. As NASA's best minds rallied together to turn this dream into a reality, numerous technical, navigational, and environmental obstacles stood in their way. Often unsung, yet vitally important, Michael Collins's role in the Apollo 11 mission was instrumental in addressing these challenges. Deep space is notoriously challenging to navigate. Pinpointing the precise trajectory to land a spacecraft on the moon's surface, given its distance of roughly 238,855 miles from Earth, required sophisticated technology and immense skill. Collins, as the Apollo 11's command module pilot, played a pivotal role here. His deep understanding of spacecraft systems, coupled with his astute piloting skills, kept the mission on course, ensuring the astronauts' safe passage to and from the moon. The moon's gravitational field is inconsistent, marked by mascons, or mass concentrations, that can alter a spacecraft's course. These gravitational anomalies demanded real-time trajectory adjustments. In the solitary confines of the command module, Collins was tasked with making these adjustments, safeguarding Neil Armstrong and Buzz Aldrin's descent to the lunar surface and their subsequent return. And there was the descent itself. Descending onto the moon's surface was fraught with hazards. The lunar landscape, with its uncharted terrains, boulders, and potential for equipment malfunctions, posed significant risks. While Armstrong and Aldrin navigated the lunar module, Collins's contributions from the command module were just as vital. He kept the home fires burning, ensuring a seamless link with Earth and readying the systems for the lunar module's eventual return. In the inhospitable void of space, sustaining life becomes a formidable challenge. NASA had to engineer advanced life support systems to guarantee air, water, and food supplies for the astronauts. While Aldrin and Armstrong were roaming on the lunar surface, Collins diligently monitored and maintained these systems in the command module, ensuring the environment remained safe and stable for the crew's survival. Consistent communication with mission control, despite the vast distance and the challenges posed by the moon's far side, was vital. There were periods during which Apollo 11, especially as it orbited the dark side of the moon, lost communication with Earth. It was during these moments of silence that Collins's resilience truly shone. He managed the module's systems, ensuring they remained operational for the return journey, even in the face of this isolation. Post the historic moonwalk, the lunar module's ascent and its subsequent docking with the command module was one of the mission's most intricate maneuvers. The precise alignment and connection of these two spacecraft modules were of paramount importance. Here, Collins' expertise was put to the test. His intricate knowledge of the spacecraft, along with his exceptional piloting abilities, ensured that the rendezvous and docking process went off without a hitch. With the lunar mission accomplished, The final hurdle was safely re-entering Earth's atmosphere. This procedure was highly sensitive. A steep angle could cause the command module to burn up, while a shallow one might send it bouncing off into space. Collins' role was once more critical. Ensuring the correct angle of re-entry and guiding the spacecraft through Earth's atmosphere was a task that demanded precision, something Collins managed flawlessly. Throughout the Apollo 11 mission, while the limelight often focused on the moonwalkers, Collins' role in the background was just as crucial. His meticulous work, unyielding dedication, and profound expertise ensured not only the mission's success, but also the safety of his fellow astronauts. The lunar landing becomes even more impressive when you consider the technology available to NASA and astronauts like Collins, especially when you compare it with what we have today. In the 1960s, the Apollo Guidance Computer, or AGC, was the pinnacle of digital achievement. With a mere 64 KB of memory and operating at 0.043 megahertz, this device was responsible for guidance, control, and navigation for the lunar landings. Remarkably, the AGC worked flawlessly, guiding the astronauts to and from the moon's surface. Compare that to today's smartphones, which operate with multi-core processors, clocking speeds in the GHz range and boasting RAM in the multiple GBs. This leap in computational power is staggering. Back then, it was akin to performing brain surgery with a pocket knife, yet NASA's engineers achieved the improbable with what they had. Also, the Apollo missions utilized the unified S-band system for communication, with data transfer rates of mere kilobits per second. Contrast this with current 5G technology, which can transfer data at gigabit speeds, allowing for real-time, ultra-high-definition video streaming. Back in the Apollo days, even the smallest data dropout could have been disastrous. The technology available was rudimentary, but worked efficiently to bridge the vast expanse of space between Earth and the Moon. Also, consider that the Apollo spacecraft were constructed using materials that were considered advanced for the time. Aluminum alloys, stainless steel, and nickel-based superalloys made up the body. Today, with the development of materials like carbon fiber composites, aerogels, and advanced ceramics, spacecraft can be lighter, more thermally efficient, and more resistant to space radiation. The Apollo missions, without the luxury of such materials, still managed to safely transport astronauts across the challenging environment of space. The Saturn V rocket, a marvel of its era, utilized kerosene or RP-1 and liquid oxygen for its first stage. Modern rockets like SpaceX's Starship are looking to use full-flow staged combustion engines, promising greater efficiency. While propulsion principles remain similar, advancements in materials science, combustion research, and computational simulations have brought about engines that are more reliable, efficient, and powerful than their Apollo-era counterparts. The crucial Apollo's Environmental Control System, or ECS, was a marvel, providing astronauts with breathable air, removing carbon dioxide, and regulating temperature. Without it, the astronauts wouldn't have lasted a minute in space. However, the system was comparatively bulky and had limited recycling capabilities. Today's International Space Station uses advanced life support systems that can recycle water and oxygen with far greater efficiency, thanks to advancements in filtration and electrolysis technologies. There is also a lot to be said about the sensors. For navigation and rendezvous operations, the Apollo missions relied heavily on human input. Astronauts used sextants, onboard star charts, and manual calculations to supplement the AGC. Modern spacecraft, though, benefit from advanced sensors, gyroscopes, and computer systems that can perform complex navigational tasks in real time with little to no human intervention. And now for another backbone of the mission: software. The Apollo software was literally woven into core rope memory by hand, a labor-intensive and error-prone process. Today, software development benefits from high-level programming languages, agile development processes, and real-time simulation environments. Software updates can even be sent to spacecraft millions of miles away, ensuring adaptability and system optimization. During Apollo's era, many of the simulations and tests were carried out using physical scale models or real components, with wind tunnels being critical for aerodynamic studies. Now, computational fluid dynamics, CFD, and other advanced simulation tools allow engineers to model spacecraft behavior in digital environments, achieving precise results with a fraction of the physical testing. The amount of data storage available during the Apollo missions was minimal. Most of the data received from the spacecraft had to be immediately analyzed or stored using magnetic tapes. Today's missions benefit from advanced solid-state drives that can store terabytes of data. Additionally, cloud computing and advanced data analytics tools allow scientists to analyze and derive insights from vast amounts of information with unparalleled speed. While the Apollo missions did have some automated systems, they were rudimentary. Now, robotics plays a significant role in space exploration. Advanced rovers, drones, and manipulator arms equipped with a plethora of sensors are common in contemporary missions. These robotic systems can carry out complex tasks autonomously, making missions safer and more versatile. All these further accentuates the seriousness of Collins's journey into the unknown on the dark side of the moon. Unlike the near side, which always faces the Earth, the far side remains mysterious, visible only from space. As Collins's spacecraft ventured into this uncharted territory, he became the sole witness to landscapes and terrains that no human had seen before. The dark, or other side of the moon, is the lunar hemisphere that always faces away from Earth, because of the moon's synchronous rotation in its orbit. It has some fascinating features that make it starkly different from the near side that we can see from Earth. The far side of the moon has many more craters than the near side because it is more exposed to meteoroid impacts. The near side is partly shielded by the Earth's gravity, which deflects some of the incoming objects. The far side also has fewer flat and dark areas called maria, which are formed by ancient volcanic eruptions. The far side has only 1% of its surface covered by maria, compared to 31% on the near side. The far side of the moon has one of the largest and oldest impact basins in the solar system, called the South Pole Aitken Basin. It is about 2,500 kilometers in diameter and 13 kilometers deep, and it covers almost a quarter of the far side. Scientists think that this basin was created by a huge asteroid or comet that hit the moon about 4 billion years ago, and that it may have exposed the moon's mantle. The far side of the moon has a thicker crust than the near side, averaging 80 kilometers versus 60 kilometers. This is probably because the Earth's tidal forces have heated and thinned the crust on the near side over time, making it easier for magma to reach the surface and form maria. The far side crust also has more minerals such as thorium, potassium, and phosphorus, which are associated with radioactive heat production. The far side of the moon is a place of silence and solitude, since it is out of radio contact with Earth when it passes behind the moon. This means that any spacecraft or astronaut on the far side cannot communicate with mission control or anyone else on Earth for about an hour every orbit. This unprecedented solitude also made his experience unique. For approximately 48 minutes of each orbit, as the command module floated around the moon's far side, Collins lost all contact with Earth. There were no voices from Houston, no static, just an engulfing silence. He once described it as a sensation of being aware of solitude. Collins was well aware of the significance of his role. While he was on the moon's far side, if anything went wrong, he would be the sole problem solver. Every system check, every reading, and every procedure had to be conducted meticulously. The success of the rendezvous with the lunar module on its return depended significantly on his actions. Imagine the gravity of this situation. If the rendezvous failed, Collins would be tasked with the harrowing journey back to Earth alone, leaving his fellow astronauts stranded. This weight of responsibility was nothing but colossal. In those moments of solitude and isolation, Collins formed a bond with the cosmos like no other. Floating in the vastness of space, with the moon's rugged landscapes beneath and the vastness of the universe around, he had a vantage point few could fathom. The quiet moments in the dark, while scary and uncertain, also offered an introspective journey. Collins, with his poetic inclinations, often expressed how these moments made him feel a part of the cosmos, an entity in the grand dance of celestial bodies. While the dark side of the moon blocked Collins from earthly communications, It unveiled the universe's splendor. Away from the Earth's bright glow, the stars appeared innumerable and brilliant. Collins described the sight as an awe-inspiring panorama. Humans are inherently social beings. Moments of solitude, especially in such extreme conditions, can evoke a range of emotions from introspection to deep-seated fears. Every moment that Collins spent on the moon's dark side was a testament to his mental fortitude. He grappled with the duality of his situation, the profound honor of being part of such a pivotal moment in human history, and the isolating experience of being the loneliest human around 240,000 miles away from Earth. To keep his fears at bay, Collins kept himself busy. He meticulously followed his checklists, monitored systems, and kept logs. But beyond the technicalities, Collins also turned to introspection. He contemplated humanity's place in the universe and reflected on the fragility of our pale blue dot. We will soon learn more about the dark side of the moon, thanks to the latest lunar rover landing on the moon by India. The Chandrayaan-3 mission, which launched on July 22, 2023, successfully landed near the lunar South Pole on August 23, 2023, becoming the first mission to do so. The landing site is located in a high plain between two craters, Manzinus C and Simpelius N. The mission consists of three components: an orbiter, a lander, and a rover. The orbiter will circle the moon for a year, taking high-resolution images and mapping the lunar surface. The lander, named Vikram, will conduct scientific experiments to study the lunar environment and seismic activity. The rover, named Pragyan, will explore the surface near the landing site and analyze the soil and rocks for their chemical composition. The rover is a six-wheeled vehicle that weighs 26 kilograms and can travel up to 500 meters from the lander. It has two scientific instruments: the alpha particle X-ray spectrometer, APXS, and the laser-induced breakdown spectroscopy, or LIBS. The APXS can measure the abundance of elements such as magnesium, aluminum, silicon, calcium, titanium, iron, and sodium in the lunar soil. 1. The LIBS can identify elements such as carbon, oxygen, hydrogen, nitrogen, and sulfur in the soil and rocks. The rover has already made some exciting discoveries in its first week of operation. It has confirmed the presence of sulfur and detected several other elements on the lunar surface near the South Pole. This is the first time that sulfur has been found on the moon, and it could indicate volcanic activity or water ice deposits in the past. The rover has also taken stunning images of the lunar terrain and left behind its imprint on the moon's soil with ISRO's logo and emblem embossed on its wheels.